All right, so in this video lecture here, let's get into the exponential functions here. So this lecture here is particularly required to be viewed after you have mastered what generally about what a function is, and you have mastered all of those details regarding a function. And so usually for a pre-calculus course, and this material in particular must be taught after you have learned and be fluent. You have learned and been fluent with what a function is and all of the details generally regarding a function. All right. So in case you have not been too familiar with what a function is, as well as how any function has a graph and all of those ideas, all of those other details generally regarding it to a function, then make sure you find or roll back to the earlier video lectures where I introduced all the concepts about any function, any general understanding of a function. So here we actually getting into one specific type of function, and so and we call those the exponential functions. But of course we are just about starting here, so I will now quickly erase the title of our discussion topic, and then we're gonna step by step get into finding out what an exponential function is. Okay. All right. So to start out with our lesson on the exponential function, allow me to just, again, as I said earlier, I assume anyone viewing this lesson has already been familiar with what a function is in general. So a function is simply just a rule. A function is simply just a rule in mathematics. And so now let me introduce the following function. It's a function. So at this point when I say function, in what you have learned, whatever I'm about to write on the board is simply just a rule. Okay, a rule telling you what to do with an input. A rule that's indicating or specifically indicating what to do with a given input. So let's now start out with a demo problem as following. How about we're given a function? How about f of x be defined with the following rule? 2 to the x. It's 2 to the x. Okay. So before we get started, before we get even any further into the function here, let me just introduce a couple of terminologies before we move on. And at this point, I did not mention anything about what an exponential function is. And so maybe you've had some background. You can hold it to yourself. Okay, and then at some point your understanding from the background will align with my teaching here in the video lesson for now. But for something like this, the rule just simply says whatever the inputs, we're gonna watch out here a little bit. We're gonna raise 2 to that input. Okay, so the input in this case so in this rule right here, the input is playing in the role of the exponent, okay, of a power. I mean, it's playing in the role of a power or an exponent, okay, of a problem. And so as that terminology I was about to point out, so for this bigger number over here, from our previous understanding, this number 2 right here is regarded as the base. Okay, so the base here is a 2, and then so now back to what I was saying in the middle of saying earlier. Now with a given input, this rule says we're gonna go from base 2. This rule here is base 2. From base 2 we're gonna raise to the exponents. So now this part right here is the exponents, or another way of saying raise to the power, the exponents, or the power, okay, as the inputs. Okay, so the base raised to the exponents or raised to the power that's being specified as the inputs right here. All right, and so now in that way, or we can write it as 2 is raised to the power x, or the exponents, the power, or another way of saying the exponents, x. But now x here is our input. That's another way of seeing it. So now I'm just simply emphasizing that everything we're seeing here is just a rule. And so nothing is violating our understanding regarding a function, and I'm only seeing this right now in my thought process. I'm only seeing this right now as a rule. The rule here is anytime we have an input specified here, anytime we have an input given, we're gonna take the base 2. For this particular rule, we're gonna use base 2, and we're gonna raise that value to, we're gonna raise that base to the power whatever indicated by the input variable. All right, so that's the rule right now. So in that way, along with our understanding that we have already learned from the earlier part of our course here, from the earlier material, then now obviously if I'm looking at say for example, let me bring in a few quick demo examples right here, that we're still on this particular rule, on this particular function, and I didn't mention what that function is, what kind of function that is. So how about we're gonna go f of 2. So now the rule says, so now we have a specific given value for the input right here. So now with this input currently being 2, that the rule says with the base 2, I'm going to raise that to the power 2. So this power now is specifically 2. That's matching with the inputs right here. All right, so now it comes back to just the easy calculation work. That equals 4, because 2 to the power 2 equals 4. All right, and then f of same function here, f of 3, for example. The rule says, so the rule of this function says we're going to start out with base 2, but we're going to raise that to the power indicated by the input. Okay, the power raised to the power x, or the power indicated by the input variable. Okay, so here that's why it's 2 to the third power. So 2 to the third power now brings us to that calculation, and with simple calculation it's 8. 2 times 2 times 2. 3 times of that identical factor to multiply together. That's why 2 to the third power equals 8. And so again, I emphasize that the way how our function here is stating the rule, then the rule is saying that we're going to raise the base 2. For this function, we're going to raise from base 2. We're going to raise to the power or the exponents being specified by the input. That's why it's x here is being in the role, is playing in the role of the exponents or the power. All right, so let's continue on a few more quick demo example problems right here. So what about f of 0? Okay, f of 0. It means the rule stated we're going to raise this base to the power 0. 2 to the power 0. All right. So 2 to the power 0, now the base here is a value that is a positive value, okay? So, and of course non-zero, because it's positive. So raised to a power 0 in algebra that we have already learned, okay? In the world of algebra, as long as the base being non-zero and raised to a power 0, we will end up with the value 1. So 2 to the 0 equals 1. We now have an output. And so I should have also mentioned throughout all of that, those times earlier, this is an output. Input is 2, and input is playing in the role of the power or the exponent in our rule. And so now according to that rule, we come out with this output correspondingly. When input was 3, the input was playing in the role of the power of that base, and now it became the rule gave out output 8. So now I have output 1 for input being 0, or x equals 0. All right. So now we can still keep going for a little further. So now what about f of negative 1? Okay. This function, in the way how the rule is indicating, then the input now is specified to be negative 1. So in the way how we have learned about raising power, we are comfortable with raising to negative power. Now it means, with our rule over here, it means 2 to the negative 1. All right. 2 to the negative 1 algebraically means 1 over 2. So this is understanding that you must be fluent already from your past course right there. Okay, so 2 to the negative power, specifically here 2 to the negative 1, it means it's the reciprocal of 2. Algebraically, so that is 1 over 2, or now numerically in decimal, it's 0.5. All right, and then Now I'm going to move on to my the other space of my board right there. So what about f of -2 right here? So now it's another negative input, a negative value for the input. Okay, this means so according to the rule stated that we're going to raise from base 2, we're going to raise to the power being -2. All right, so again, from your past understanding, 2 raised to the -2 as a calculation problem, this is now simply 1 over 2 squared. And now we can see that as 2 squared in the denominator is a 4, so it's a 1/4. This is our final answer, or numerically as a decimal, okay, it's a 0.25. So this is output with inputs -2. This was outputs being 0.5 corresponding to that input -1. All right, so the rule for this function here that we specifically investigated, that was the rule being, you know, the 2 to the x, okay, 2 to the x. So the x is the input, 2 to the x. All right, and then we tried a different various inputs, a few different inputs so far. So what caught my attention so far, and I will get into this more specifically, but as far as the way how this rule is stated, then this function can take any value of x, okay? Any value of x. I tried 2 and 3, but more generally, I want viewers, I want students of mine who are watching this lesson to understand that these are representing positive numbers. So any positive number is fine, okay? This function can also take input being 0. It gave out an output value just fine, okay? This function can also take negative inputs and giving us an output, right? And the output here is still being a positive value, even though it started to get into the decimals. All right, and then with a different negative inputs, we had an output here. All right, and so now allow me to also go a little forward, and I still didn't even get into any of the naming of the function, what kind of function this is. I didn't even get to that, and I did not even mention what exponential function is, even though we know that we're currently looking at that topic about exponential function. But all of a sudden it seems like I took you off track, okay? We'll get back to the on track later on. But now briefly allow me to show you how you can, because at this point surprisingly there's still a good number of students or learners who are not too comfortable with calculating all of these, and especially later on when it gets to those kind of inputs where it's starting to become because so far I've used only whole values input, so the calculation can be done mentally, okay? But now my intention here is that there will be times where we're gonna learn to put in an input where, of course, from base 2 we raise to an input, a power input, but then it's like a decimal. So for example, if we are asked to calculate the following, the function value at 0.5, when input appears to be a decimal, well, according to the rule, it means 2 to the 0.5 power. Okay, 0.5 is a 1/2. 0.5 is a 1/2, so it means 2 to the 1/2. But we're still beating around the bush. We didn't get to a final exact numerical answer. And then with our experience from algebra, we understand 1/2 here is a square root. So yes, this is the same as square root 2. Okay, but then what exactly is the decimal value for this? Okay, or even this is still easy to recognize. What about we're looking at a power 1.5, for example? Actually, that's still a little easy. 1.67, for example. Okay, 1.67. Well, according to the rule, it means 2 raised to the power 1.67. But now, how are we going to get the final answer out of this in terms of a computational final output? So I'm saying that what I'm saying here is that we will have outputs, but what exactly will those outputs be? And so now that's where, now allow me to swing over to the computer station here to quickly show how we can operate with our calculator, our standard calculator. So throughout many classrooms on standard, we use a TI 83 and 84 calculator, okay, for these calculation purpose right here. So let me quickly swing over to and put the calculator on screen right here to show how you can operate with your calculators, your standard calculators that are mostly used in academic classrooms. Okay. All right. So now with on my standard graphing calculator here, now for this particular emulation that I'm using right here, it's an actual computer program that is an emulation of the TI-84 plus CE version. But whatever functionality that you see here on the screen will be exactly the same as your own TI-83 or 84. So your standard 83 or 84 will work exactly the same. Okay. So to calculate those values, raising power is this key right here. Raising power is this key right here. So earlier when I was doing those raising power when the power was a whole value, for example 2 raised to the power 3, okay, then what I did there, again let me clear all this out, 2, and then I type hat, okay. And so for this particular software right here, for this particular software, the program is advanced enough that anytime we hit the hat key right here, it brings the cursor here into power mode, superscript mode right here. And then we enter power 3, okay, and hit enter. All right, so the answer is 8. That's how we that's how we operate with the calculator using basic. Using just the hat key and using just a standard TI-83 and 84 calculator. And now for that exact same problem, but for some, I'm still sticking with the TI-84 plus right here, the TI-84 plus CE, but for some users, for some TI calculator users who are using an older TI-84 or an TI-83, then when you raise power, your screen may look as following. So for example, I was doing that 2 raised to the 3rd power, or 2 to the 3rd. Here's how we're typing it in. 2 to the 3rd. But the older calculators will not put you in superscript mode. That's completely okay. Just 2 hat 3. All right, and that will give you the answer after hitting enter. Okay, so I'm just trying to show 2 different versions of the operating system with the TI-84 or a TI-83. And now let's advance to try out a few more function evaluation, a few more calculation problems on this calculator so that we can get comfortable with the way how we calculate it. So earlier on the board I was going with 2 raised to the -2 power, okay? So now notice that I'm back to that the advanced version of the TI-84 plus where it puts us in superscript mode right here, okay? And now hitting enter. That gives us the calculation, the final calculation results being 0.25. And for people who are using the older calculator, if you would like to enter a negative exponent like you have just now seen, then here's how we can do it. 2 raised to the power. And for the older operating system with the TI calculators, we won't be put into superscript mode. So here's how we can handle it. 2 raised to a. Now make sure you type in parentheses, and now negative sign is here. So -2. Okay, this is for those users, those calculator users who are using an older operating system on your TI-84 calculators or the TI-83 calculators. And so now we hit enter. It gives us the exact same answer here. All right, and so now just like that on the board, now I intentionally wanted to show the following. So what about when it was on that function f of x equals 2 to the x? What about when it was f of 0.5? So now we go 2 raised to the power 0.5. Okay, and now hit enter. All right, so this value here is the actual decimal, which is also the same as the actual value of square root of 2 right there. Okay, and so the square root of 2 here, according to that, what we have seen on the calculator, yes, square root of 2 is 1.4142 and a lot longer. All right, so this is the actual numerical decimal. Okay, and then let's now try the 2 raised to the power 1.67, because this is way beyond, these are now way beyond our mental math capability. So we need to start turning out turning out focus to the calculator to ask for assistance. Okay. So now on the calculator, now hopefully at this point anyone viewing the lesson has had a good a decent amount of comfortability with the calculator at this point, and now I can just use the advanced version of the TI-84 plus CE right here. And so now 2 raised to the 1.67. Okay, and now I hit enter. So this is the value right here in numerically in decimal expansion right there. All right. All right, and we are still not done with this function yet. It's a function. Now we have learned that it's a function. It started out with having a base here, and now notice. Now with this base here, allow me to erase all of the notes I've made earlier, because so here in this rule, okay, another detail here to understand. It's not the same as x to the power 2. It's not the same. Here our function says, the rule says we raise, so base is 2. We raise to the power being the input. But something like this, it's a simple quadratic, or the base here is the x, the input is the base, and then we raise to a power that's given. So when we see a function like this value here is fixed once it's given. That value 2 right here, that power 2 for this function, it's fixed once it's given, once the function is defined. So if we had a function g of x equals x squared right here, this is just our friendly and familiar quadratic function. Or in case anyone have learned prior to this lesson about the power function, and this is the power function. Okay, and it works different. So here, if we give an input, we're gonna raise the input. We're going to keep the input as the base, and then we're going to raise the input to that given power. So this power right here is given, or I said fixed. Okay, given, or I mean fixed, or it's given. So once it's given, we cannot change it. That's the idea. Okay, but here, the base is fixed. The base is the elements that once it's given, it stays fixed, it stays permanent. We can change this base to different powers. We can change this base. I mean, we can raise this base to different powers depending on whatever inputs indicated here. That's the difference right there. So in these two functions are majorly different in a sense that, you know, what's the role of the inputs is playing. Okay, in a sense that what role the input is playing. All right, so clearly I have to also state that. And now let me also put away this note right here. And back to our function. We're still not quite done with 2 to the x. Okay, so now the way how I say it is 2 to the x. We have done a few calculating values like that. Okay, so now let's put all of those, let's summarize all of those into a table of values. Because in the end, and I still did not mention any name of what kind of function this is. I'm saying this function, the way we read it out, it's 2 to the x, and we have already operated with that fluently because we know the rule so well. We just already know that a function is a rule, and so this is our rule. Okay, and then we try through a few input values, and so now I'm going to organize all of those inputs values in a table. So how about the x here? We tried x was -2 and x was -1. We tried with input 0. We tried quite a few, and so now in a certain order, how about -2 was the lowest input we ever tried. Let's put it in for our x column right here. Okay, and then my input -1, we also tried with that, and input 0, and input 1, okay, and we even try input 1.67. We even try with the input, 0.5, but you know my table here is getting short, so allow me to leave that out. Okay, and I just want to emphasize we also tried the input 1.67. But again, I'm a little bit under the pressure that we have short board space here, so I'm going to leave 1.67 out of this table. But just realize and be aware that those inputs has a place, any of those inputs has a place on this table. Okay, and so now we also try x equals 2, and we also came to x equals 3. These are all the inputs that we have tried particularly. All right, so in our calculation based on the rule, so now let's just summarize it. Okay, so this is now y value, or just whatever the outputs for this function. Okay, so when x was equal to -2, we had 0.25, or numerically speaking, 1/4. Okay, and I even showed the calculator technique with these. And so now, when this was -1, we had 0.5 as the numerical value for output, and then this is equivalent in fraction. It's 1/2. For anyone learning with me in pre-calculus, I personally favor that you are fluent with working with fractions. Fraction is a nature that as long as you still continuing going further and growing further into mathematics, fraction will live with you permanently. Okay, so and even if you don't plan to go further than pre-calculus in your mathematical career, fraction is still playing an important role in your daily life out there. So get comfortable with fractions. Okay, when x equals 0, we came out with output value 1 here. Okay, when x equals 1, we came out with output value being 2. When x equals 2, we came out with output value being 4. When x equals 3, we came out with output value equals 8. Okay, what is my intention at this point? What's my intention at this point coming up with this table of values? Well, because I mean, since we already sketched down a few calculated values here. Now I put that into a table of values because here's my intention. Well, as we have now fluent from our understanding about function generally, then any function has a graph. Any function has a graph. Okay, specifically at this point of the lecture, I won't get too far into graphing into studying intensively about the graph of any the exponential function yet, and because I didn't even introduce what this function is. Okay, but as far as calling this as a function, as far as agreeing upon this, as far as agreeing that this function is a function, doesn't matter what kind of function that is. We already had a table of values, a brief table of values. Let's just now look at the graph, because like I said earlier, any function, as long as we agree that it's a function, we're convinced that it's a function, it will have a graph. Okay, and so I will now put this table of values into a graphing space right here. I'm gonna bring this table of values into a graphing space, and from there we're gonna recognize, I'm gonna plot the points here. I'm gonna see x value, y value, x value, y value. And so I purposely, as a thought process, I purposely want to bring my viewers back into those early days when the earlier generations of mathematicians were specifically learning about this kind of function, starting out with a 2 to the x. Okay, so let's have a look at that. All right, so now on my graphing space with the graphing utility right here, currently it's empty. All right, so now I'm gonna put in those values that we have already put on the table. All right, and now this point right here is indeed extra. So I made my graphing utility to do a little bit extra work compared to what I show on the board. But now let's look at all of these right here. First of all, this point right here. Now I'm showing the coordinates. Now I'm showing the x and y value. It's x equals 0, y equals 1. Just like what we had here. X equals 0, y equals 1. All right. And then moving on to the next one. When x equals 1, y equals 2 from our table of values. So now on the graph, that's how we have this point right here. This point when x equals 1, y equals 2. And then just like that again. Now when x equals 2, y value equals 4. Just like that table of values were listing right there. Okay, and then when x equals 3, y equals 8. Okay, And then I did not have x equals -3 on our calculation on the board here, but I made my graphing utility to go a little bit extra like that. All right, so just like that, when x equals 3, y equals 8. And now, so after sketching out a few points, and then so when x equals -1, we came down to 0.5. Now the graphing utility I'm using here is not able to give us, and that's why we are the human being. We need to be better than machines. And that's why I highly recommended my students or anyone viewing the lessons here is to be to be fluent with your fraction skill. But see, even calculator here, a lot of those calculators, they won't have the capability to show fractions. Okay, so just something for us to be aware. But when x equals -1, okay, machine is showing 0.5, but really for us here it means it's 1/2. So -1 for x, 1/2 for y, and then similarly with this point right here, -2, that point right there, -2.25 for y, or in fraction it's a 1/4, positive 1/4. Okay, this extra point, anyone viewing the lesson here can quickly calculate that and put that on our table that I had on the board earlier as well. When x equals -3, okay, then the machine gave pointer 125. This means it's a 1/8. Okay, this is a 1/8 right here. You can go ahead and use the table of values. You can do a quick calculation to verify. Okay, and you don't have to wait for me doing this. You can quickly do a verification on that on your own calculator skills, and you can have 2 raised to the -3 power, and then you should be able to verify how it gave -3 comma pointer 125. Okay, so now don't misunderstand my intention about this. I am not showing I'm not showing anyone viewing this video how to use any graphing utility to put up the graph. I just want to use this graphing utility as a way to describe if we were doing the graph, if we were one among those early generations of mathematicians exploring the graph of this function for the first time, then I'm using this, the simulation right here, I'm using this, the graphing utility to demonstrate the idea of how we can do that if we were doing that as a hand sketch version. Okay, so right now my intention is not to show anyone how to use technology to quickly put up the graph. Okay, so think about, we had our first part of the process down. We put the plot points from the table of values down. Okay, so now these are all the plotted points of the table of values. So if we would sketch that, then of course from the left to the right, we now notice these points seem to form into a shape that's not linear. It's kind of bent. Okay, it's kind of bent. It's going slow. It's rising slowly for those points to the left of the y-axis, but then it starts rising quickly. All right, it starts rising vertically and rapidly when those points go to the right-hand side of when those points appears on the right-hand side of the graph or the right-hand side of the y-axis. All right, so in that way, here's how I can sketch that. If I have paper and pencil, here's how the sketch would look. We just simply try to connect our best as a curve that's going through these points, that's all. And we're trying to make it from the left to the right. So for a human being, normally I would start with a few easy points, say right here at the intercept right there, because we do have a point right on the y-axis. I can start making a curve going through those points. So pretend that if we were doing this by hand, that's how we sketch that. And then we're going to try our best to draw the other parts that's going through these points, going that way. So that's how I see it. And now we have, and of course, I'm not saying that the graph stops here, but if we were doing that with paper and pencil, this is about far enough that we can have a good, clear understanding of what the graph looks like. All right, and so now I'm going to make that a little further out. But ladies and gentlemen, this is now the complete graph. This is now the graph of 2 to the x. The graph of 2 to the x has that shape right there. Okay, the graph of 2 to the x has that shape. All right. So now, ladies and gentlemen, we are ready to know what an exponential function is. So I brought in that term This big number 2 right here is called a base. Okay. This is big number 2 is called a base. The variable part right here is the input. Yes, that's the input, but this is playing in the role of the exponent. Okay, or the power. All right, it's the exponent and the power. So now the question is this the only rule where it's taking a base, well, the base given here is a base 2, but is this the only function where you see a given base and then raised to a power being the input of the function? No, it's not, because in the way, and anyone learning this lesson here should be mature enough to understand that sometimes, some other time, we can have a function given as 3 to the x. It's similar with this function in a sense that once the base is given, once the function is defined and given, the base here is fixed. This is base 3. Okay, earlier this one here was base 2, but the base once given, it stays fixed. The element that's changing is the inputs playing in the role of the exponent. Okay, so the exponent is here. All right, so it's similar in that way. We have the fixed, the constant base, fixed constant base. Okay, and then the inputs, the changing element is the input, which is playing in the role of the exponent. So the exponent is what's changing. Okay, the exponent is changing depending on whatever inputs that being specified. Okay, so make a note there. The exponent is changed. Okay. By different inputs. All right. So we change the exponent from different inputs from one input to another input. And that's the idea. So that's one similarity, one thing in common between these functions. Okay. And then we can have another one. Think about it. We can also define a function as following. All right. So how about h of x? So it looks like all we do is just creatively come up with a fixed value. 3, 2, okay, or so you can think about a 0.5, okay. And right now, a further common thing between these bases, they are positive number. Let's stay on that, along that side right there. We pick a positive number, okay. Positive. It's trying to get decimal here, but it's positive number, positive number, positive number, and then we're going to raise that positive number to the exponent being the input of our function. Okay, so here we have this one here. We have base 0.5. So 0.5 here, once given, it's the fixed base. It's a fixed base of our exponential, of our function. Okay, and then this here is the exponent. All right. And so now 3 little examples I brought up so far on the board here. So now they all have a constant base once given, and then the rule says we're going to raise that base to the indicated exponents. The exponent is indicated by the input. All right, and so now in that way, let's get on to the other board and write down a formal definition. All right, so as far as a definition, okay, a function, or any function that's given by the following formula, given by the following rule here. Okay, we can call that y equals f of x, or equals some base a, okay, raised to the x. Okay, so earlier in my demonstration I was using base 2, so 2 to the x, 3 to the x, or 0.5 to the x. So those are the 2, the 3, or the 0.5 being the bases. That's what the a here generally is when we're trying to recognize what it means by an exponential function. So now a function given by that form, that's what we've seen earlier. Okay, any of those functions is called, so now we formally use that name, is called an exponential function. All right. Any function in that way of being defined with the f of x equals some base a raised to the x power. Okay, but the x power here is the input of our function, of our rule. So if any function given by that form a to the x is called an exponential function. Okay, of base a. All right, an exponential function of base a. Okay, and so I'm not completely done with writing down the definition, but allow me to put a pause right here, okay, about this definition right here. Okay, so let's go back to the other board. So this function now is legally called, this function 2 to the x is now legally regarded as an exponential function. It's base 2. All right, so this function now we call that an exponential. Right? This function here is exponential function of base 2, This function right here is called the exponential function. All right, of base 3, just like that. And so this third one on the list right here on my left, on my board right here, okay. And I can erase these extra writing right here, extra note. All right, so this function, yes, now we call that as an exponential function. Exponential function, okay, of base 0.5. All right, base 0.5. Okay, so now at least throughout these 3 quick little demo problems I brought up right here, I used a base, as you notice, positive bases. Okay, so the rule that I use here, positive base, and positive base. 0.5 here is a value that start looking decimal. Of course, our minds naturally work better with whole values like these bases here, but when we're considering what to be an exponential function, the base doesn't have to be nice whole value as long as the base here so far is being positive. So now here's a couple of things to pay attention to. Okay, let me now erase this part on the board. So with those I put here on the board earlier, the bases were positive. But before we formally put that into our definition, let's have a look at some other potential candidates that can be regarded as an exponential function but eventually fail here. Let's say if we're looking at a -1 to the x, for example. This could be a function. It could be a function. Don't get me wrong on that. It could be a function. Okay? Could be a function because as long as we give an input and we have an output and each input gets exactly and only one output, we have a function. So I'm not saying that this is not a function. That's not what I was saying. But now with this function right here, the base, in the way how I define the function like this, the base is -1. Okay, so let's have a few investigation problem here. For a function for a rule defined like this, if we go f of 1, okay, f of 1 input equals 1, and the function goes -1 raised to the first power, which is -1. Here's the output, okay. And then when f equals 2, f of 2, when the input equals 2, that's what I meant. This is -1 square, okay. Now remember, the base in this case is -1, so when you raise a power, you order of operations. According to the order of operations, we have to multiply that -1 with -1 again because it's power 2. Okay? And so now it's +1 as it turns out. Okay? +1 as it turns out. And then Now we raise it to the third power, okay? Then it gives, so negative 1 to the third power is negative 1. Okay? And then when we go with, with a negative, I mean 0 first, okay? When it go with the 0 power, we're looking at negative 1 to the 0 power, okay, which is a 1. Okay, the base is a non-zero value, so raising that to a power 0, we're going to end up with a 1. But now when the input is like a 0.5 right here, okay, things start getting complicated. It means a square root of negative 1 because, well, I shouldn't rush anyone learning right here, but think about negative 1 to the 1/2 power, but that means it's the square root of negative 1. We start getting out of that zone where we were comfortable with numbers right here. Well, unless you have already learned some imaginary number, but that's not what we learn here at pre-calculus, then this is undefined. So some inputs starting to get, thrown out right there, okay? And then when we get to see some other inputs, say a negative 3, okay? It's a negative 1 raised to the negative 3 power, making it 1 over the negative 1 to the third, and making it negative 1. And then when it gets to a negative 2 powers, we have a 1 over square root of negative 1, another undefined. So it's starting to get a little scary. It's starting to get a little scary. And then when it gets to square root of negative 0.5 right here, okay, then it's going to become 1 over square root of negative 1. And this is another undefined. Okay, so this function right here, I'm not saying that I'm not saying that we can't work with that. Okay, I'm not saying that we cannot work with that. Again, that's what I have to emphasize. It's a function existing out there, but it's a lot more complicated than those we brought up earlier, and it's all due to the fact that the base here is a negative base. Okay, the base here is negative base, and so in that reason, we don't want to include the negative bases in our family of the exponential function. Like I said, I'm not saying that we won't be able to work with this function, but it's a lot more complicated, and it has a lot of exceptions compared to those standard exponential functions. And so in that way, anytime it comes to negative base, we take them out. Okay, we take them out of our consideration. And so now, back in this case right here, an exponential function of base a here, that definition that I put a pause in the middle right there. Now I'm going to come back and complete that. Okay, provided we only consider a function like that to be an exponential function. Anytime our base is a positive number, not even equal 0, provided a, the base here, is a positive value, okay, not even 0. Okay, so why is that? And of course, whatever I'm about to explain here will never be detailed enough until you've learned more and gained more experience as you progressing through math right here. But again, we can also define a function f of x as 0 to the x. Okay, but when we go f of 1, it's 0 to the 1, output is 0. When it's f of 2, 0 to square, it's 0 again. So you can see that as long as we stay with these, or with a decimal to the 0.5, 0 to the 0.5, 0 again. Nothing too fascinating about this. That's one of the reasons why we take this. See, this is base. It looks similar. It looks similar to that form a to the x, but if we purposely define a function with base 0 to the x right here, the output is a lot of times boring. The output is a lot of times not fascinating at all because it's all 0 out. And then all of a sudden there's that specific point right here, 0, where 0 raised to the 0 is, it takes, at our level here, let's call it undefined. Okay, but it takes another level, okay, a whole other level to study about 0 raised to the 0 right here. Okay, so all of a sudden everything is plain old 0 for outputs, and all of a sudden when it comes to inputs being 0, it comes to something really strange here. And like I said, it takes a whole another level to understand this. And then when it goes to, and then all of a sudden it completely rule out all the negative. It means we can do this, we're all undefined after that. And so as far as the inputs, it doesn't agree with all the other. See, 2 to the x I brought up earlier, it works with all inputs, positive, negative, and 0. 3 to the x, it works with all inputs, positive, negative, and 0. I did not try 3 to the x on the board formally, but you can spend your own time doing that as well. Okay, but any of those are 2 to the x, 3 to the x, or 0.5 to the x. They have all that common input values that we can use. I will get formally into the idea about domain, but as far as that idea, the domain of these functions are the same. But the domain of this is all of a sudden completely different, that does not agree with these. And that's why we don't want to. For that purpose, again, I'm not saying that this cannot be a function. Nope, I'm not saying that. But just simply because it has so much difference with the other function right here, where it's a base raised to a power of, these are positive bases raised to a power. Okay, but this particular 0 raised to a power is too different with those other functions like that. So as far as a formal definition of being an exponential function, we don't want the base to be 0 as well. So we take away the case where the base is negative value, and we take away the case where the base is 0. So now back in our formal definition, provided a, the base, anytime we consider an exponential function, we're only interested in working with base positive or positive base. Okay, positive base. And then even further, and the base other than 1. The base is other than 1. Okay, so I will get back and explain a little more about this later. Okay, about why. So now we're all clear. I brought up as many as many examples as possible, pinpointing out the reason why when base equals 0 or a negative base are not considered as exponential function. Okay, that's just we're trying to keep things simpler for us. And then I will get to the explanation of why we're not letting a equals 1 as well later. All right, but this is now a formal definition of what an exponential function is. All right. So now we are ready to head into our first example. All right, so in the first example here, let's just get ourselves comfortable with recognizing whether a given function can be determined as an exponential function. Okay, so here, this is example 1, and allow me to write down the worded instruction of this example 1 right here. So let's determine if the given function is an exponential function. All right, and so this problem, you can also see this as a way that we can look at that and be able to classify the function given, whichever the function about to be given here. We're going to learn that skill to classify the function can be recognized as an exponential function. Okay. All right, so in that way right now, let's one more time look at the formal definition of the exponential function, the formal definition here. So any function in the form of a constant base raised to a power x, where the x here came out from the input of our function, is called an exponential function. But we have a requirement here. Our base here has to be a positive value, and that base is other than 1. Okay, so at this point I still have not explained the reason why we don't want to consider exponential function when it's base 1 right here, and we will get to that. But as far as right now, anytime we have a function in the form that a given base and raised to a power, and the power is the input of our function, and then along with that requirement where the base has to be a positive number other than 1, okay, that is well determined as well classified as an exponential function. All right, so now let's head back to that example 1 right there, and then we're going to be given a few different functions for us to determine. All right, so now in part A of the example, let's look at, so how about the function as following, f of x equals, so the rule of this function says 10 to the x, 10 to the x. So now once understanding about this, to understand a little further about this function, about this rule over here, because again we're about to determine if this given rule, if this given function can be regarded as an exponential function. So what do I see here? We have this base here, once given, it stays the same because the changing component, the changing element is only the exponents right here, according to the whatever different inputs we're assigning to it. And so it has a base being raised to the power, being raised to the exponents, and the exponents changes depending on whichever inputs we're giving it. So we're close. We're more than halfway firm that this function is an exponential function. But then let's check with even further to make sure that it meets the requirements. So the base here has to be a positive number. So we do have this base here being a 10 positive number. All right, so 10 is a positive number. Okay, so it meets that requirements, and also 10 is other than 1. Okay, so it also meets that requirement, and now it's also in that form of raising to a power, the inputs being the power, being the exponent. So now this function here, okay, there are many ways of saying we can put a check mark here saying that yes, it's an exponential function. We want to classify whether the given function is an exponential function. So now, simplest way of saying I put a check mark there. Okay, or we can just say yes, it is an exponential function. All right, and so in practical time, if you are on an assignment, I mean this is not only for my class but for any class, if you are taking a course and where you start learning about exponential function, there will be a problem here and there among your assignments where for either from the textbook or as an online assignment, it's all about there will be a problem somewhere here and there, like this problem right here, where a whole bunch of functions is given at you, and then which one among those is classified or is defined as an exponential function. This is how we check for that. Okay, and so once you are confirmed that your function is an exponential function, you can either put a check or select yes. There are so many different ways how you can answer this depending on the formatting of your problem. They're either given as a textbook problem or as an online web assignment problem. Okay, all right, so now let's head out to another one right here. So in example 1, we're still deciding, we're still learning our way to determine if a given function is an exponential function. So how about let's look at part B right here. Let's look at the following. So how about a function f of x being defined as, so how about a 1.5 being a constant and then raised to an x. So the rule of this function says for whatever inputs given to the function, we're going to take the base 1.75 raised to that inputs. So the input is again being the exponents or the power of that for that base right here. Okay, so now we're already at this point. This is consistent with the definition of what an exponential function is. But we further need to also make sure that these two requirements are satisfied or fulfilled. Okay, so now back in this problem right here, then yes, 1.75 as the base is already a value positive. No one can argue about that. Okay, and then 1.75 is clearly other than 1. Okay, so that's another requirements that passes. So it's in a form, it's in an exponential form. It's in the forms where it has a given base, and once that base is given, it's raised to the exponents being the input of our function. That's what it is, first thing. And then the base is positive and the base is other than 1. Now we're good to go. This function, now you can say, you can put a check mark if it would be a sort of like a web assignment problem, or an online generated math assignment problem. Or you can, if it's on paper, you can say, yes, this is, as a short answer, this is an exponential function. All right, let's look at another one. So so tentatively, the plan here, I am going to be giving out a few, okay? And some of those came out just straight out from my own creativity. But then I'm gonna show my thought process so that anyone can really get a solid skill in determining whether a given function can be an exponential function or not. Okay, so let's look at the next one. All right, so the next one here, part C right here. Let's look at, how about f of x given here to be, how about a -3 to the x. All right, so again, looking at the form, the setup, the definition of the function, then we're looking at a given base, a given value, a given number being, or a given constant being the base. And then that base is raised to a power x, where the x here is the input of our function. Okay? And so the exponents here is the input of our function. It's the changing element. Okay, so again, it looks like we're over 50% firm that this function is an exponential function. Okay, however, we have to be cautious a little bit to make sure the base here meets the requirements, the two requirements actually. So the two requirements need the base to be positive and the base have to be other than 1. Okay, our base is other than 1, so that meets the requirements. However, this base being a -3 fails big time the other requirements. It fails this requirement. The base being positive, it failed this one right here. And this requirement is even more critical than the other requirement actually. All right, and so in this case right here, now as far as classifying that as an exponential function, nope, not this time, not for this function. Okay, so it looks close. Okay, close enough to be an exponential function, but in the end, that base itself fails this requirement, so that can't be an exponential function. Okay, so now, if this problem is a written problem that needs to be corrected, okay, and that's how you present your work right there. Okay, and then usually if this is an online problem, an online generated problem where you do your online math assignment, then these are just thought process. You only need to quickly answer yes or no. That's whether this is an exponential function or not, or you put leave out a check, clear the check box or something like that. All right. And I still have a couple of other ones. So how about part D right now? A different function here. So f of x equals 0.25 to the x. And so this one here is very similar to that earlier one I brought up where it was 1.75 to the x. The base itself starting to go decimal, quite scary decimal, 0.25. Okay, but in the end, it's in the form of a constant base and raised to a changing exponent. And the reason this exponent is changing is because it's the input. That's where the input of the function is. Okay, so depending on different inputs, we have a different exponents. And so 0.25 constantly raised to different exponents. That's why this one here, at this point, recognizing that form like the a to the x form, we're over 50% firm that this is an exponential function. However, again, let's cautiously check for the other requirements to see if this function meets with those other two requirements right there. The base needs to be positive. In this case, is that so? Yes, it is. The base being 0.25, it meets the requirements. Being a positive, the base must be a value other than 1. Okay, other than 1 just simply means not equal 1. Okay, it's less than 1 here. 0.25 is less than 1. I agree. I noticed that, but that's not important. So now all I see is 0.25 is other than 1. So now this function also meets that other requirement. So now for this function, I'm saying yes. I put a big check mark depending on the format of your problem, of your how your problem is written, and then or you can say yes. Okay, either put a check or you say yes. This is an exponential function. Okay, so let's try another one. So here let's look at f of x equals x to the 10th. Okay, it dangerously, and I brought this up in the earlier discussion of this lecture as well. It has that dangerous form as well. It has a power, it has an exponent, it has a base. So this x here is the base. There's base raised to a power. There's base raised to a power. It was the whole discussion so far is all about there's a base being raised to a power, being raised to an exponent. But the major difference here is that the base is the changing element. The base for this function is the changing element, depending on whichever different inputs we're giving it. So when input is 5, it's 5 to the 10th. When input is 3, it's 3 to the 10th. When input is -1, it's -1, all in parentheses raised to the 10th. So in this way, how the function is defined, see, like I said, if it's a -1, we change the input to a different value. It's -1 to the 10th, okay? And then, or when it's f of 5, we change to different inputs. It's 5 to the 10th. And if it's 3 for the inputs, it's 3 to the 10th. So the base is changed depending on the input value, but then the power, once it's defined and given, it stays fixed. So this function right here is clearly not like those we had in the definitions. Yeah. So this is clearly not an exponential function. Okay, because being an exponential function, we first thing require the base to be constant. The base is constant, and the exponent is the changing parts depending on the input variable. But here the base is changing already, and then the power stays the same. Okay, power is constant. So as a matter of fact, see, a function like this, in case you have already learned this lesson after you have learned through my lecture about the power function, then yes, a function like this is regarded as a power function. Okay, so this is just for you to know. But if you have learned it or you have not, you will get there within this pre-calculus course as well. Okay, but this is okay for anyone who have not learned formally about the polynomial or anything like that, then this function here specifically is called a power function. But if you all have already learned about what a power function is prior to learning about exponential function, then you don't need this. You don't need me to inform you about this. Okay. So in other words, this function here is clearly not an exponential function. Okay. So I put a big cross away. It's not an exponential function. Nope, it's not. It's a power function. All right. So let's now look at another one. All right, so let's look at part F of the example. So how about f of x equals 0 to the x? And clearly I brought this up in that demonstration earlier as the reason why we don't want to include base 0 among our exponential functions. So needless to throw in any defending reasoning. I use that term, the defending reasoning. There's no reason to defend that this is an exponential function, or there's no reason to reject because it's already not an exponential function. Okay, so we just straight out of the box. Nope, this is not. Okay, there's no reason to further defend that. Hey, it somehow can be an exponential function. Nope, it's just not. We need the base. We need the base to be positive, but here our base 0 is equal 0. Just failed already. All right, and so now that one was a quick one. Let's look at another one right here. All right, so at the end of this one, you will start getting some reason why right here, some explanations of mine. But how about 1 to the x? All right, so 1 to the x. So clearly this violates the requirements that the base is other than 1. The base is 1. Is it other than 1? No, it's not. It looks, at this point, it looks quite convincing that it's exponential because it's got a constant base raised to a changing power being the input of the function. But then in the end, it fails immediately that requirement. It already passed that requirement that it's a positive base. It passed that requirement, but then in the end, it failed this one right here. Okay, it failed this requirement that it has to be other than 1. Okay, so I talked a little bit about, we will get an explanation here. Here's the reason why. Okay, so, and when we get to graphing an exponential function, you will have even more, a much more, inclusive understanding of this. Okay, but right now, just think about this. How about if g of x equals 1 to the x, then g of 1 equals 1 to the 1 power, which is 1. G of 2 equals 1 to the square power equals 1. G of 0, so positive number all gives 1. G of 0 equals 1 to the 0, which is 1 as well. And then g of a negative number, like negative 5 right here, equals 1 to the negative 5 power, which is also equals 1. Nothing fascinating about an exponential function where base equals 1. And that is the reason why now in these days that is indeed the reason why we ruled out that case where base equals 1 right there, because with base equals 1 it's kind of pointless. And now this is only part of the reason. You will get to even better explanation when you get to graphing of an exponential function and see why it's anytime it gets to exponential function we only take base positive and a base other than 1. All right. And so now at this point right here, we've been exposed to different bases throughout our example 1 and throughout all of those demo problems earlier. So as far as being the bases, so I emphasized it already, and now I want to emphasize it again before I push that into the next idea right here. But you see, as far as the bases, okay, let's focus a little more into the basis of an exponential function. So with a base, I brought up 2 to the x as that problem to promote the idea right here, and base here was it's a positive not equal 1. Okay, base 2 whole number. I also brought in, even though I did not talk much about it, 3 to the x. This is base 3. Okay, and so the base here, base 3 is a positive base other than 1. Okay, I also brought in 0.25 to the x. The base here is see, the base is a 0.25. It's positive, it's other than 1. This was part of our example 1 that we finished earlier. Okay, this is a equals 3, this is a equals 2. Okay, so now, and you start seeing it's the base now no longer in the way how we define an exponential function. Then there's nowhere throughout that definition. Nowhere throughout that definition requires the base has to be a whole number. All it says here is as long as we are in that form where we have a constant base raised to a power where the power is being the input of our function. And then that's over 50% of the definition already. And then all we need is to stay under that requirement where the base has to be positive and the base is other than 1. But nowhere is saying that the base has to be whole number. And so in that way, it was completely legal that I had this kind of base as long as it met that requirement. Okay, so that's why specifically now let's look at the basis of the exponential function to find out a little more. So I also brought in 1.75 to the x as the base. See, this is another example where the base went decimal. Okay, the base of our exponential function went decimal, equals 1.75. Because again, now I emphasize the base of an exponential function does not need to be a whole value like this. Okay, whole value is good. It's good for our mental math, but in the end, legally speaking, these bases work too. There will be applications out there where the bases are decimals. The basis of an exponential function is a decimal. Okay, so in that way, as a larger impact here, now, as long as we have a base, anytime we have a base anytime we have a number being a positive number and the value is other than 1, that number can be legally the base of an exponential function. Okay, I repeat, anytime we have a value that's positive and other than 1, then that value can legally be the base to an exponential function. So in that way, as that impact I was about to point out, you see, everybody knows the pi value. It's a constant that's well known to the history of human being. It's related to measuring circle. Anywhere that deals with circle, there's a pi. Okay, so numerically speaking, it's a constant and it stays 3.14, okay, 3.14, and a lot longer. I'm not too worried about how complete that decimal is, because it's hopeless to find a complete decimal of the pi, but it's a 3.14 something, a lot longer. Okay, it's a constant known to almost everyone. We are introduced to this constant since our very early age. Learning about math. I mean, in these even modern day, public schools are starting to teach children at about the 3rd grade or the 4th grade the number pi right there. But I mean, I just want to point out how important that constant is. And then but now for us here, looking at that in a more general understanding, pi with its value like this, it's clearly positive. It's clearly other than 1. And so in that way, this pi right here well deserves its place. This pi will well deserve its place to be an exponential function, base pi right here. Okay, so I'm not saying that we will see this kind of function often out there, but it's completely legal. Okay, if we have a function pi to the x, it's completely legal, an exponential function. Okay, so anytime that you're looking at a problem and your professor, your math instructor, or you're looking at, or you're working with anyone on math and specifically about exponential function, and you run into a problem pi to the x, you gotta start accepting it. It is completely legal to be an exponential function. Okay, and I'm not saying that the output is going to be a nice looking. The base itself is already so irrational. Okay, the base itself is already so not nice looking, and so we cannot expect the output value of a function like this is nice. But in the end, it's legally an exponential function. Okay. All right, so I just want to briefly emphasize that as long as we have the value, a constant, or a value being a positive value and other than 1, we can take that value and make that an exponential function. And that's it's a good reminder for anyone who plan to define your own exponential function. Okay. And so now, since I got pretty far into that way about the bases, what bases are accepted, right, to be the base of an exponential function. Okay, so now allow me to introduce another value right here, the exponential base right here. Okay, so I'm still leaving the pi here. And I mentioned this earlier. The pi is long known to the human history. Pi is long known to the human history. Okay, but aside from this pi value, aside from this pi constant right here, there is another constant also well known to human math on Earth right here. Okay, another constant also as well known as pi. Okay, to human math on Earth, but it's not as long known as a pi. So pi came out since from the ancient time. Okay, since the Egyptians, the mathematicians, and the Greek mathematicians. But then the number I'm about to introduce here, very well known, and it keeps getting more and more popularity. But it's not having a history as long as the pi number. Okay, so that mysterious number I'm about to bring up is the E number. Okay, the E number here, the value for E. Now, so for anyone learning in calculus, this is maybe the first time you hear about this. There are PhDs out there who study about the number E right here. Okay, so what you know here is never enough. Okay, but you just know a few things enough for you to move on in the course like that. And then again, as I said, you have a whole journey in the future waiting for you to keep looking at this E number. Okay, so E itself, as like I said, it's similar to pi. So pi has a value constantly being 3.14 a lot longer. E is another constant known to human being. Its value is a 2.718 and a lot longer as well. 2.718. Okay, for anyone learning pre-calculus, this is where it starts first. This is where it all started out. How did mathematicians come up with that number? It takes, like I said, it takes a whole completely different journey to come up with the history and the historical development of this value right here. Okay, that's why I said there are PhDs who learned this. Okay, but now as far as to make it easy for any of our learning purpose right here, we only simply take that, hey, this is another value, another constant known to human being aside from the pi right here, and it has a value being a positive 2.718. Okay, so yes, the pi, you have heard that since what, 3rd grade, 5th grade, but we need to wait until somewhere the high school senior math or somewhere 1st or 2nd year college math to start knowing, start being aware about the constant pi, the constant E right here. Okay, it's named E as a credit to Euler, who invented that number right there. Okay, and it's not even him who was the original person who had that idea, but he was the one that built that formal formation of that. Okay, so now, and what I introduced this as a simply now taking this as a positive value and a value other than 1. And so now, if we define a function, e to the x right here, this function is an exponential function. All right, this function is well qualifying to be an exponential function, simply because the e, the base itself, is positive. The base itself is other than 1. And so as long as we're having a constant value or a value positive and other than 1, we can legally define an exponential function using that base right there. And as I said earlier, with this base right here, and particularly built from an e to the x function, it has a huge application among the business and social economic problems out there. Okay, any math problems in business and social economics problems, okay, it built on this. And that's before I'm mentioning those applications in science right there. Also has a lot of math problems that built from this e to the x function. So never look down to that. Okay, see, pi is a well-known, very well-known constant, and then it's heavily related with circles. But then the function, the exponential function pi to the x, is not seen too often. E to the x doesn't have that application with circles, doesn't have that relationship, that close relationship with circles. But the function e, so e constant itself doesn't have that close relationship with circles. But e to the x as a function, as an exponential function, has a huge amount of applications out there. It goes from, like I said earlier, business math courses or business math problems to social, the economic problems, the math problems, and all kinds of science of math problems like the chemistry, physics, okay, and of course in math. All right, so it has a huge amount of applications for e to the x function, and you will have a long journey, even way beyond pre-calculus, to explore the applications of e to the x. All right, so as far as just beginning of our journey right here, we're simply going to take that as another exponential function that we know that it exists out there. Okay, and then at some point in the quarter, I will start turning our focus mostly on this e to the x. And then this course here being designed as being designated as a pre-calculus, that means it's time that we start taking this function seriously, so that when you go to your calculus course, you won't be shocked where your professor there will only focus anytime you hear about exponential function. Yes, it means any of these as a whole family, but then most of the time your professors intentionally talked about the e to the x as the only one representation of all the exponential functions out there. Okay, so I just want to give some brief but still in-depth enough emphasis on the importance of this e to the x function as an exponential function right there. All right, and so now we now at this point, that's all I need you to know. Okay, e to the x is a well-qualifying exponential function out there, so don't get shocked at any time it got brought up to your attention. And one more thing. So just like the pi to the x, I am never gonna expect the output value for e to the x is going to look nice, just because the base itself is already looking so nasty. It's looking so crazy. 2.718, and I have to leave dots because we will never know the ending of this complete decimal. There has never been a successful ending to search for the ending of that complete decimal. Okay, and so for that reason, when we have e to the first power e squared or e to the -1, with those values right there, they're never going to be nice looking. Okay, so that's one thing to be expected. All right, so now after I gave that brief introduction of the e to the x function as one member among all of the other the exponential functions like that, and now let's push that into another example. Now we're ready for heading out to another example. All right, so before I start into this example right here, example 2, okay? It seems like just a simple problem, but it's a skill where many textbooks do not emphasize. But I chose to emphasize this skill. It's not a hard skill, but it's a skill where if I don't emphasize that here, when after my class and when you arrive at calculus course, you will be shocked with the amount of times you use the skill at calculus. Okay, so for that reason, allow me, even though at this point learning about it, it seems like just another thing your professor here in this lecture is putting into your mind right there, but then when you get to calculus right there, this skills will all certainly be used very often, a lot more often than you expect. And so I just want you to get a good preview of this skill so that later on when you arrive at calculus, you won't be shocked. Okay, so it's simple at first, and then it's going to gradually get more challenging and more challenging. So how about actually I missed some other details. So start out with just let f of x be defined as an exponential function 4 to the x, and then upon defining that function, let's evaluate. Okay, so this is the worded instruction of our example 2 right here. We start out, so generally you might run into another problem where your exponential function here is different base. It could be e to the x in your assignment. It could be the 2 to the x in your assignment, in your test, in your whatever. Okay, the generality here, it's an exponential function. And then I want you to evaluate the following. Okay, so now part A. Let's evaluate. So one problem, but I give a few little subproblems at once. So how about in part A, I'm asking you to evaluate f of 0, f of -2, and f of 1. Okay, so really this is one part A of the example here, but we'll have 3 tasks to do. So f of 0. So now the skill I want to emphasize here is that, see, when we give a different input right here, that input goes into the exponent. I mentioned this earlier, but now it's time to do this example to really emphasize that. So now f of 0 means the rule of this function says 4 raised to the input. 4 raised to the input. And so the input now is going to replace or going to substitute for our x in the formula, in the function. Okay, so 4 to the 0. So now legally speaking, it's as a computational problem, 4 to the 0, algebraically equals 1. So this is our final output numerically. Okay, so I just want to emphasize that anytime we're giving an input to the exponential function, it seems ridiculous that I'm emphasizing this now, but I have seen students arriving at my calculus course, but sadly still struggle not knowing where to substitute a value like this, an input, into an exponential function. And for that reason, I decide to step a little bit aside from the textbook and emphasize on this particular skill right there. Okay, so and the problem here is still simple. It will gradually get more challenging and more challenging. But keep that fundamental. Anytime we change to a different input, that input goes into the power and substitute for the x in the power. All right. And so now once you've got that the word of mind repeated enough a number of times, let's continue. So f of, in this part area here, we have a few other tasks to do. Let's evaluate f of minus 2. So now I switch, see, generally input x, but now I give specifically x equals negative 2. So that means I am going to take this input, substitute that into that x right there. So now that becomes 4 to the negative 2 power. 4 to the negative 2 power. Okay, and so now as a purely or simply as a computation problem, then 4 to the negative 2 algebraically means it's 1 over 4 squared right there. Okay, that's just the algebra of that in case anyone doesn't have a calculator resource immediately. Okay, but then that means this is a 1 over 16. Okay, all right, so as a fraction we're leaving it like that. Okay, and then as far as actual numerical value, then it's 0.0625. All right, and so now I'm showing both ways, both formats of the final answer here, in case you are asked to present in either one of the two forms here. Okay, so watch out in your very different assignment problems. Some assignment questions ask you to leave your answer in exact fraction, or in some other assignment problem it's asking you to leave your answers in decimal. So I'm leaving that here in my lecture here in both forms. Okay, and so now there's another task for this same part area here. So how about f of 1? See? So now once again you have seen that twice throughout the part A of the example here. So we change the inputs to different values. And so whatever the input is, whatever the value assigned for the inputs, assigned to the input, we're going to take that input value and substitute that in place of the x right here. Okay, so that means here it's 4 to the first power. All right, and so 4 to the first power is simple enough. It's just 4 to the first power equals 4. So I brought this up to emphasize, okay, to highlight again that anytime we have a different input, that input goes into the power, okay, and replaces the power. Throughout all the 3 little problems we did here, we never changed the base. We never changed the base. All right, so enough with that. Let's move on to another problem right there. So we're still in example 1. We're still in example 2 right here, but let's move on to part B of that. All right, so part B of the example. Again, let's together evaluate. I'm going to put in about another, one same problem here, but a few different tasks. Okay, so how about f of 3 plus h? And then as well as evaluate f of minus 2 plus h. And this is where things get even more heavily, more heavily confusing for students, sadly even at my calculus course. Okay, because the students, when they're seeing this from an exponential function, they become very unsure what to do with the expression here. Okay, and this is the reason why right at the beginning of our lesson here I emphasize that this lesson must be learned after you have learned about all details regarding how you can generally operate with a function. Okay, so I've had all of that details well, before we got into this particular lesson where I introduced all of the general ideas, including how we can evaluate a value into a function, into a rule, specifically when the inputs became an expression rather than a value. Okay, and so now, but at least throughout the work here, you will get some of those skills reminded again. You see, what we have here is no longer a number, a numerical value for inputs. Like in part A, life is still easy, life is still simple, because it's a value and we know where to go, we plug that in. Okay, but now it's no longer 0, it's no longer -2, it's no longer 1. It's a 3 plus h. The input here is an expression instead of a numerical value. But see, I already emphasized this in part A, and we're doing that same thing again, that exact same thing again. I'm going to take the whole, I am going to underline this whole thing right here. Okay, so f of 3 plus h, after underlining that, I just want to point out that we're going to take the whole thing that I emphasized right here. We're going to substitute that into our function. So for text inputs 3 plus h, that's what happened. For text inputs 3 plus h. And that's all there can be. That's all there can be. I'm not even asking you to simplify or anything like that. All I need you to be aware of is now once you are given an input, and be ready that the input is starting to get more than just a numerical number, a numerical value, like an expression like this. Then all you do is take that expression, throw that right into the place of your input variable x right there. So instead of x, as usual, now it's 4 raised to 3 plus h. The whole 3 plus h is in the superscript position. All right, so 4 to the 3 plus h. And you're not even asked to simplify or anything like that. So this is about the ending of our problem right there as an expression. Okay, so it seems scary at first, but in the end, that's all it is expected that you know how to do. So for the other task right here, f of -2 plus h. So now I'm going to start picking up the pace a little bit. Now I'm going to take the whole highlighted expression right here. I am going to throw that into the function. So now see, and in my style, anytime I'm substituting a value, I always start out using parentheses first. So instead of x here, I'm going to put in all that -2 plus h. I dump the whole thing, the whole expression here, right into that x and replace for that x. That's all there is. All right, and so now it becomes a 4 to the -2 plus h. All right, that's another final answer for us. That's another final answer for us. All right, so let's now head out to part C of the example. All right, so part C of the example, we're looking at how about evaluate f of a plus h, f of a plus h. Okay, f of a plus h, and then times and another task here to be done right here, f of x plus h, f of x plus h. All right, and so now with this one right here, so very similar to part B. Whatever we're about to do here is very similar to part B, except for there are completely no numerical expression at all. It's just a plus h, and here is x plus h. There's no more 2, no more 1, no more 3 involved. Okay, it's just an expression entirely in terms of letters. So letters, letters, letters. Okay, but now starting into handling the first task right here. This a plus h is one expression, and it's in a way how the functional notation is indicating, right? And this is where it's required that you have already been fluent with function notation right there. So we're going to take the whole input here, the whole a plus h, as one package for the input. I'm going to substitute that, throw the whole package into the place of x right there. Okay, take the whole package here, throw that into the place of x. So in that case right here, our function is 4. Okay, the place of x here is right now empty, so now we throw the whole a plus h in there. So now in the superscript position is 4 to the a plus h. Okay, and then we can just simply write that as 4 raised to the power a plus h. All right. That is a function. I mean, that is some final expression. And I never asked in this problem, and this problem never asked for simplifying it. Okay, and so that's where we finish with our problem. So I only brought up this problem to show my intention to have you emphasize on that skill that anytime you have that whatever input it is, and specifically when you're working with an exponential function, simply just take the whole package, take the whole input, whatever that is, either a number or an expression, take the whole thing, substitute that into the place of the x. Okay. So let's do the other task for this particular problem in part C right here. So f of x plus h. Okay. So just like that, I'm going to take the whole underlying expression right here. I'm going to throw that into my function. So it's now 4 being raised to the power x plus h. That's how it is. And then without the parentheses, it's going to be 4 to the x plus h. We're good to go for that one. Another simple one. Okay, it's simple, but it sadly has that elements that I don't know why a lot of students, when they arrive at my calculus course, as I said, they arrive at my calculus course but still unsure what to do with an input other than a value or just simply an input, unsure what to do to an input when we're giving it to an exponential function. So here it is. That's the only thing that we need to do. All right, so let's get you even more comfortable with that. All right, so in that way, in part D, one more problem being introduced in this particular example right here. So how about the same problem in part D right here? Let's do two tasks. F of 3x plus 1. Okay, and then f of x squared minus, or I mean plus 5x minus 1. All right, so that was our part D of the example. It's that same task right here. I mean, there are two tasks in here, okay? But then the work is the same as in part C and part B that we were doing earlier. What we have here is no longer one single number. We have an expression, okay? And so this expression here is just for you to notice right here, that 3x plus 1. So now, as we're about to tackle down f of 3x plus 1, I just want you to remind you and raise your awareness that this is another this highlighted, underlined 3x plus 1 right here. It's another function of x. Okay? It's the 3x plus 1 itself is another function of x, but that's not really important. Now seeing that whole thing here as an expression being in the place of the inputs. So now our function is 4 to the x. So now I'm going to substitute the x. I'm going to throw the entire function of x here, the entire 3x plus 1 in place of my x. So 3x plus 1, now substituting for it. All right, and so now in this case it's going to be 4 to the 3x plus 1. 4 to the 3x plus 1. All right, so ladies and gentlemen, so with this particular part D of our example, I want to introduce a little further the intention so that eventually I'm going to lead you into the next understanding. But see, at the end right here, 4 to the 3x plus 1, we can define another function just to be 4 to the 3x plus 1. Okay. So generally looking and compare with the fundamental form, this function, I'm not saying that it's an exponential function or not. I'm not saying that yet, okay? But this function at least it has some similarity with the original exponential function here. Well, clearly this one here is an exponential function. It meets all that requirements of our, it meets all of those requirements from our definition for being an exponential function. It has a base, a constant base, constant base. That constant base is raised to a power that's changing, the exponent that's changing, okay? This one here has base, positive base, positive base, base other than 1, the base other than 1. But here's the thing, be careful. This function here is raised to the form of a something more than just an x. Here is f of x equals 4 to the x. Here is f of x will equal to 4 to the 3x plus 1. So the whole expression here, the whole expression of x as a function of x right here is being in the exponent form here. And so for this particular one, I'm going to say eventually it's an exponential function as well. Okay, even though you already realized, you already noticed through the final expression that it has even more than just x. Because our definition only involved base to the x, base to a single x, not even a 2x, not even a 3x, but what we have here is a 4 to the 3x plus 1. So think about as the order of operations. Eventually, if we're substituting a value for x here, then x must be multiplied with 3 first, and then plus 1. We have to take care of all of that in the exponents, and then we're going to raise 4 to that final exponent, and that's the idea here. But now, so it looks in the end quite different with 4 to the x. But now I'm telling you ahead of time a little bit. This will eventually be an exponential function. We will get to that point where you get all of that explanation later. Okay, but for now, this one here, if we regard that as a function of x, it's also an exponential function of x. Okay, we still have one more task to be done for this part D of our example. All right, so now for this function 4 to the x as an exponential function, if we go f of x squared plus 5x minus 1 here. Okay, so now in our experience, now we can just easily and simply take that entire expression that I underlined here, take the whole thing, substitute that into our function. So now it becomes 4 to the x squared plus 5x minus 1. Okay, and so this function right here, this final expression is the final answer to our problem here, to our task here that we're doing. But then in the end, 4 to the x squared plus 5x minus 1, we can also regard to this as a function g of x, some function depending on the x input. But now think about it, if we're giving an input to x right here, then we're going to first, according to the order of operation, first we have to square the x and plus 5 times x minus 1. And get that done first, get that quadratic part finished first. Come out with whatever value, and then we're going to go 4 raised to that power. Okay, and so now in that way, it is clearly a function of x. But now this function, unlike the 4 to the 3x in the earlier problem right here, 4 to the 3x plus 1, this was eventually, I said earlier, this would eventually become an exponential function. This would be classified eventually as an exponential function. But this one here, with the square there involved in the exponents part right there, this is not an exponential function. Okay, it's not an exponential function. All right, and we will get to see the reason why to that. I mean, it all has that base right here raised to a varying, a variable exponent. But then how come this one here gives eventually the whole thing would be considered as an exponential function, whereas this one would not be an exponential function? All of the explanations will come as we explore the actual graphs of these exponential functions. Yeah. Okay. All right. And so now at this point, and right after I have already introduced about the e to the x function, now allow me to lead into example 3 right here. All right, where it's going to be extremely similar to example 2 that we just got out of. So let's now look at example 3. So the worded instruction is given as follows. So about f of x equals e to the x. Once we have cleared that e to the x is legally an exponential function, and I have mentioned in-depth details enough that it will have e to the x function. We have a vast number of applications out there. Then let's start paying some good attention to it. So I'm going to start out with some example over here. So let f of x define as e to the x. Let's evaluate. All right, so evaluate. So now part A, very similar to example 2 that we've finished. So how about f of, let's calculate, let's evaluate f of 0, f of 1, okay, f of 2, f of -1, and f of -2. Quite a few tasks being asked here. Okay, and so now f of 0 is where it's e to the 0. So now drawing the experience from example 2 right here, then we can just get things done in a much more sped up, pace right here. So this is 1. Doesn't matter what value of e is, but now it's positive and it's other than 1, a constant raised to a 0, a value raised to a 0, a non-zero value raised to a power 0, that equals 1. So that one's easy. Okay, now f of 1 equals e to the first power. But see, so now what exactly is e to the first power? Let's explore. As far as exact expression, that's all we can have. It's the number e itself. It's 2.718. Okay, but now I only showed 2.718 on the board earlier, but not able to show further expansion. So now let me really swing over to the calculator to show you, to demonstrate how you can get the actual e value on the calculator. Okay, and I'm using for instructional purpose. I'm asking my students to use the standard TI calculator, the TI 83 or 84. Okay. All right, so now with a standard TI 83 or 84, okay, to calculate the value of e right here. Okay, so right on your keypad, right above that key with the sign, with the label ln right here. Okay, right above that key, ln, then there's the e to the x feature right here. So to access e to the x feature, we go second ln, so that now is e to the x. So now it's this, at this stage right here, at this point, the calculator is ready to accept some input. So earlier on the board, I was calculating e to the first power. So e to the first power technically means e to the 1, or it just equals e. So now hitting enter, that is also the exact value. And it's not even the complete yet, but this is, I shouldn't even say exact value. This is just the more accurate value of the e constant compared to what I wrote on the board. I only wrote on the board 2.718, and then I left out all of these. And this is not all of it yet. This is nowhere near to the complete. And like I said earlier, we have never completed that the decimal part of this e value yet. But this is now, so e to the first from the calculator is legally the way to obtain the true value, okay, of our constant e. All right. And now f of 2 equals e squared. Okay, and so now we really need to look it up. I mean, we really need to look for help from the calculator. Okay, so now with the calculator, e squared, I'm going to go second e to retrieve the e function first. So this is, so the calculator, we already know that this is going to be that constant value. Now we raise to the square power. So e squared. Now hit enter. All right, so this is the value. So when I'm writing this down, I'm about to use just 3 decimals, but how far to round, do watch out for that in every different assignment question right there. All right, so e squared is about or approximately 7.389. Okay, and then about just 1 more decimal, then it could be a lot longer. All right, so that's e squared. So you may be asked to leave your answer in exact expression, then that's all we can do. It's e squared. Okay, and then other than that, if you're asked to leave your answer in decimals, that's 7.3891, and or maybe longer. That's you choose your own rounding depending on how the problem is asked. Okay, all right. So now f of 0, f of 1, f of 2. We still need to get to f of minus 1 and f of minus 2 right there. All right. So now f of minus 1, that equals e to the negative 1 power. Okay, and then e to the negative 1 power is the same as 1 over e. So we can accept this as final answer in exact expression. And then if anyone is asking you to write that in decimal, let's now swing over to the calculator on the computer station right there and to find out how we can get it done. All right, and now with the calculator, it's second ln. Okay, and so now I'm typing in. So this key right here is for negative sign. So negative 1. Okay, so e to the negative 1 power. All right, so it's 0.3678 and 7 and a lot longer. Okay, so now on my board I'm only going to round to 3 decimals, but you can write down further depending on however long the decimal rounding is. All right, so that is 0.368. Okay, if we round to 3 decimals. But I said again, watch out for your rounding requirements in every different problem. Okay, so now the last one here, and that was our answer there. So now e of negative 2. Okay, I mean f of negative 2, and so that means e to the negative 2 power. Okay, we take the inputs here, we put that in the place of the x, just like that, just like how we were working with that 4 to the x earlier, that exponential function earlier. Okay, so now that means here we're looking at 1 over e squared algebraically, so we can stop here in exact expression. We can also stop there. It depends on how your instructor wants it. I mean, I'm assuming that this is for students who learn with me, but there are also, who knows, there are also other students outside of my class but learn from my video here. So you got to watch out for how your professor or your professors want you to express your final answer in exact format. There's still even more than one ways of expressing it in exact expression. But now as far as the real numerical value, okay, so approximately it is equal to, all right, so now second ln, now I'm putting in minus 2. Okay, so e to the negative 2 equals to approximately equal to 0.135. And here I'm about to go with 3 decimals, but watch out for your rounding requirements in your actual problem out there. All right, so approximately 0.135, and that's the answer in numerical decimals right there. All right, so we've done part A of the example. So it's just to give you some experience with working with the ugly looking value like the e right here, but it's completely possible to get it done, and it's actually very likely that you see this function a lot throughout the rest of the course, on the rest of our time on exponential function, and when you advance to a higher course like starting with your calculus courses, then working with e to the x function will be a lot more intense. Okay, and so now let's get in part B of the example. All right, so for part B, I'm asking, or the problem is asking us to evaluate about f of 1 plus h, okay, and then f of minus 1 plus h. All right, f of 1 plus h or f of 1 minus 1 plus h. So again, take this problem as similarly as how we were doing that with example 2 right there. So now when we get to this, f of 1 plus h, the input is no longer a number. The input this time is instead an expression. Okay, it's an expression. So in that way, now in what we have experienced up to this point, all we do is just take the whole expression here, being the input. we're going to throw it into our function. So our function is, the rule says it's constant e raised to the input. So the constant e raised to the input 1 plus h. We're good to go. Okay, and that means now we have e to the 1 plus h. And that's about good enough. All right, just only really just one step. I show that extra step because it's my habit that I always put a substitution in parentheses. So I had to produce the next step to take the parentheses away to declare that was our final answer right there. Okay, and then so f of negative 1 plus h. Okay, so this would be e to the now minus 1 plus h. And then that here is e to the negative 1 plus h. That is our final answer. Okay, nice and simple. Even though it could be tricky for someone. So now it's just a reminder that anytime you see an input, doesn't matter whatever that input is. There were even times throughout a face-to-face class, I even made joke with my students. Even if you put a dog here, for example, instead of a number, instead of a negative 1 plus h, like there's the f of a dog right there, then you can just take the dog as the input and put the dog here. Okay, so e to the dog, whatever that is, and if we can operate with the dog, then it's going to give you an answer. All right, that's just how important we know how to operate with this, input. So now that's done with part B. All right, so part C of the example. So let's look at, okay, and I'm repeating this part like in example 2 right here. How about f of a plus h? And then here there's f of x plus h. Okay, and so now f of a plus h. So now our function is base e raised to the inputs, but the input is now the entire expression a plus h. A plus h that I just now highlighted. So now it's e to the input, so the input is a plus h. I put it here. All right, and now I'm just going to produce an extra step to take away the parentheses. So it's e to the a plus h. We are good to go. That's our final simplified expression. We really didn't simplify anything. Okay, and now let's look at the other task of this same problem right here. How about x plus h? Okay, f of x plus h. And so now again base e we raise to the inputs being x plus h. So substituting x plus h into the place of my x right here, then I have to use parentheses. So consequently I'm going to use one more step that shows how I take away parentheses. Take the parentheses out. All right, so now it's e to the x plus h. All right, and so that's part C of the example. And so let's even put in one more problem. All right, so part D of the example. How about f of 2x minus 1? And then in the same part D right here, that's another task here to be done. How about f of x squared minus 3x plus 1? Okay, f of x squared minus 3x plus 1. Okay, so f of 2x minus 1. I just need you to realize that this whole part right here is the input. The input is not only a nice number. It's not an easy expression. It's a function. Okay, it's a function of x. Okay, fair enough with that. But in the end, whatever function of x or whatever, but it's an input. It's an input to our function f. So now I'm going to take base e. Okay, and wherever I see my inputs, I'm going to substitute the inputs. Instead of x, I'm going to substitute that with 2x minus 1. That's how it started. Okay, and then now I'm going to simply just take the parentheses away. So e to the 2x minus 1. This is our final answer. This is our final answer. But then furthermore, I would like to emphasize that e to the 2x minus 1 can be regarded as another function of x. And it's not the same with f anymore. That's why I call it g of x. The x here is the input of another function. Okay, but then in the end, at the end right here, soon enough you will learn that as a conclusion, this function is also an exponential function. Okay. Even though it looks already quite different, here we only have one simple x, but here it's some other function of x. And this one over here would eventually be an exponential function if we would classify it. Okay. But then for the next one, so now let's look at the next one here, f of x squared minus 3x plus 1 in this example. So in a way how it has been ever since example 2 until now, then it's now going to be simply e to the, so all that x squared minus 3x plus 1, the whole ugly looking expression. Because it starts getting big, that's all. So it looks quite ugly looking, but in the end we take the whole package, dump that right into the place of the x right here. And that's why I have parentheses out here. Okay, sort of like as an empty package, we put the whole x squared minus 3x in plus 1 inside of that package, inside of that empty space right there. So now taking the parentheses away, e to the x squared minus 3x plus 1. And that's as far as final answer, we got that there. Okay, we got that done. It's nothing big about the problem other than just take a whole package, substitute that into the variable. Okay, but now again for our journey here, sooner or later you will hit to that point right there. But see, e to the, if we just simply look at e to the 3x, e to the x squared minus 3x plus 1 as a function, then yes, it's a function, it's another function aside from f. It's not the same as f, it's a function of x, a different function of x. And then there will be some point where students and people generally start confusing that this is an exponential function because, gosh, it has that base e and being raised to a varying power. Okay, so it looks almost like an exponential function. Plus this thing here has that base positive and other than 1. But then really this one here would not be classified as an exponential function. Okay, and we will get all of that solid reasons later on. Okay, so here it's just all about classifying who's is classified as an exponential function and who is not, and in case function gets even a little more complicated and start looking like the one we have here, but then in the end this one here would not be an exponential function. Okay. All right, so that's everything we have for this example 3 right here. All right, so now at this point you have seen enough, and I brought that in scatterly here and there throughout example 3 and example 2 and example 3 earlier. So now let me erase this and write in a few things right here. All right, so we looked at 4 to the x, and then we had 4 to the 3x plus 1. Okay, these are all now function of x. Function of x. Let's call that a different name. We can call that g of x. And then we have 4 to the x squared plus 5x minus 1. This is some h of x. Okay. And then now here I can call that a function, some function. How about p of x being e to the x from example 3 right there. And then we came to q of x being e to the 2x minus 1. Okay. And then we came to the r of x being e to the x squared minus 3x plus 1. Okay, and so these are all having some similarity in a sense that they all have a base, and the base is constant. Okay, and then the exponents, the power, either a simple expression in a power or a more complicated expression in a power. But then some of those were called, well, for these they are strictly and they are definitely exponential functions, as we already know. But these we just now learned that they are exponential as well. Okay, exponential for this one and that one. But then these two are not exponential. Okay, these two are not exponential, even though they look almost similar to these, almost the same, except for the expression here is quadratic, whereas here is linear. Quadratic here is it's linear. Okay, so these two are not exponential here, just because the expression in the exponents part right here, they are quadratic. And so now in that way we actually come to an extended version. We realize that there are actually more members we can put into our family of exponential functions. I will get back to this and point out the reason why we consider more of these, okay, as exponential function, meaning we include more members in the exponential functions family, and the reason why we leave these guys out right there. Okay, but now I'm going to swing to the other board and I'm going to come up with what's so-called the extended definition of an exponential function. Okay. All right, so now we're going to call this an extended definition. Of course, it's an extended definition of an exponential function, so that now more forms of an exponential function can be recognized. All right, so now let's look at that in the following. So a function, or any function, all right, a function that's given by, all right, so how about f of x, or we can also call that y equals f of x, and then primarily f of x equals a to the mx plus b. The base raised to a linear function, raised to the power, raised to the exponent being a linear function, and this exponent is a function of x. Okay, and this form right here is exactly what we saw throughout these two little example problems I brought up earlier. Okay, the exponent has, in the exponent here, it has a linear expression there, a 2x minus 1, a 3x plus 1 here. But here it's a quadratic, so we just don't consider these. As far as the reason why we do this, we will get to that explanation we will get to that. Right now I'm just extending the definition that we can include more forms of an exponential function. Okay, but then exactly why we include more members in this family of exponential functions, you will get that explanation in the later part of our learning about exponential functions. Okay. And so now back to the halfway completed definition, extended definition of an exponential function. So any function in the form of a base raised to a linear function like that. Okay, and then even further, it has a constant coefficient in front. So c, or c times a to the mx plus b, and then plus with a constant. All right. So something like this is also called, or just now generally called, an exponential. All right, an exponential function. As far as the name, it's just exactly the same name as how we've had that in the earlier definition, an exponential function of a base, or maybe I should write this in the next line right here, of base a. All right. And then again, in the same requirements. Okay, as long as, or provided the base has to be a positive value and the base is other than 1. All right, so these are the two requirements that was there when we had our original definition of an exponential function, and here in this extended definition we still carry over that the two requirements there for our exponential function. Okay, and so this is indeed the more general form. Okay, this is more general form. This form right here. This is a more general form of an exponential function. So yes, if you call this a general form, I would agree with that as well. Okay, it's a general exponential function. Okay, whereas the earlier one that I've had as that definition, the earlier one where we simply just had, you know, an a to the x right here, and a is positive and a is other than 1. Yes, it was an exponential function, but now, you know, there are people who call this a simple exponential function. Sorry for the shorthand writing being used a little too intensively here. Some people call that simple exponential function. Somebody call that basic exponential function. I agree with all. I agree with both, because these refer to the building block of how we can come with this general exponential function. All right, and so now one more time, let's turn over to this board right here. So in this extended definition of a general exponential function, then the one I wrote here, I would like to just rewrite it so that we can see more, we can get more of the space down here. So that function g of x equals 4 to the 3x plus 1. See? So now, obviously, that a value is 4, because if we're trying to align this with the given form, c times a constant base raised to mx plus b plus a k right there. Okay, then the base is 4, just like that. The coefficient for this is 1, because really this function is the same as 1 times 4 raised to the power of 3x plus 1. And then we don't see any extra constant added to it, means plus 0. So that means now it's the k is 0, and then now in the exponents part, m equals 3 and b equals 1. Like that. All right, that's how I recognize this function being one of the general exponential functions. Okay, and then similarly, we were looking at the e to the 2x minus 1. Okay, that's function, that q of x function, when I wrote that down in the list earlier. So see, the base here is e, and then raised to the mx plus b, so it's 2 times x plus with a negative 1. See, mx plus b right there, and then it has a coefficient 1 in front, because seeing nothing in front means it's a coefficient 1 always, and then plus with a 0 constant. So now a is e, that base right there. Okay, and then the m is 2, the b is negative 1. All right, and then the constant coefficient in front is a 1, and then the coefficient at the end is a 0. Okay, and that's how I'm breaking these functions down, so that it aligns with the general form, okay, of a general exponential function. Okay, so now let's take that into example 4. All right, so in example 4 here, allow me to introduce the worded instruction as following. So let's evaluate three tasks right here, or 3 problems as following. How about evaluate f of 2, f of 0, and f of minus 2. Okay, but we didn't have the functions given. Okay, thus here comes the function. So evaluate f of 2, f of 0, and f of minus 2 if, so that depends on different functions we're given here. So if f of x is defined as 3 times 2 to the x. All right, so there you go. So this is now, we were in this example where our exponential function clearly is an exponential function. It's in that form. It's one of those general exponential functions. This is c right here, and this is a to the x. Now the part in the exponents here is simple. It's not the mx plus b. This is really 1x plus 0 right there, and the c is 3. All right, so just want you to follow with that. So now that means when we get into this designated calculation, f of 2 means. So just like that, that's why I purposely walked you through example 2 and example 3 earlier. So now first thing in line, when you in the way how your function notation is reading, it's indicating that 2 here is the input. So we want to take this 2, substitute that into the place of our input variable here. So that means just simply write it in 3 times 2 substituted by 2. So 2 substituted by x, 2 to the x, but substituted by 2 there. Okay, so now it's as far as the mathematical work, 3 times 2 square. 3 times 2 square. So, and now at this point, I have to remind anyone this famous thing ever, PEMDAS, the order of operations. We have to always take care of things inside the parentheses first. Okay, parentheses, and then anything that's in the exponents, we have to finish first. And then once we're done with exponents, then we're going to do multiplication and division. It comes about the equal priority, but always after exponents. So multiplication or division. Okay, and then A and S stand for addition or subtraction. These two are about the same order. Okay, that's PEMDAS. It's short for, this is a fixed scheme, okay, for order of operations. So in this way right here, there's multiplication, there's power, there's exponent. So we have to raise that to the power first, and then we're gonna multiply. All right, so that now gives the answer simply 12. That's our final answer, okay, because 2 squared is a 4 times 3 is a 12. All right. And then same part A, but we have a different task. And so to maximize my board space, allow me to erase the extra notes right here. I only want to leave just that PEMDAS here to remind anyone. So f of 0, okay, so just like that, I'm going to substitute 0 into the place of my x right here. So it's 3 times 2 to the 0. So this time we have a clear direction of where to go. We have to raise 2 to the power 0 first, which gives me 1. And so 3 times 1 is done after, or in the end, it's 3. All right, and so now one more task left for this particular problem. How about f of negative 2? All right, so that means 3 times 2 to the negative 2 power. So 3 times 2 to the negative 2 power. So let's lay down some math. First, I'm going to just take away the parentheses. So 3 times 2 to the negative 2. But see, and that tells us to take care of power first. So it's 3 times whatever comes out of this. It's a 1/4 in fraction. And then 3 times 1/4 comes out being a 3/4 right there. All right, so we can leave that as a 3/4 in fraction or 0.75. Two different ways of expressing it, but that's how we're done with part A of our example 4 right here. Okay. And now let's look at part B right here. So we're still asked to do f of 2, f of 0, and f of negative 2 right there. The intention here is we want to generally see how we can evaluate these functions at a 0 value, at a negative value, and at a positive value. That's all. Okay, so how about we're going to do the same tasks here on a different function. And that's what part A, part B, and part C is for. So how about in part B we have f of x is defined as 2 to the x but over 5. Okay, 2 to the x but over 5. At first sight, it's hard to recognize this as one function in that class right there. In this class of c times the exponential a to the mx plus b plus c right here, it's hard to recognize our function 2 to the x over 5 is in this family. But now let me do some algebra work right here. And at this point, it is extremely vital that you review all of your elementary algebra skills right there. So now we have a fraction. Well, it got 2 to the x. That's not important, but it's a big thing. It's a fraction. Okay, so I'm going to rewrite it as a 1/5 times 2 to the x. Now I clearly display the following nature. We have a coefficient, and that component, that exponential component is there. All right, so 1/5 as a coefficient times 2 to the x. So the mx plus b thing is 1x plus 0. That's what it is. Okay, and then plus a k here means a plus is another 0. All right, so now f of 2 equals 1/5 times 2 to the 0 power. Okay, and 2 to the 0 power is just 1, so it's now 1/5 times 1, it's 1/5. Once we understand the true nature of the function, we get it done easily. Okay, next one, f of and so 1/5 times 2 square. Okay, now that means, so 2 square is a 4, so it's a 1/5 times 4. And so that was after the parameters right there, the order of operations. And now 1/5 times 4 is nothing but just a 4/5 right there. All right, so that's how we had it done. The next task in the problem here is f of 0. All right, now that means it's 1/5 times 2 to the 0. So think about it. We just simply substitute the designated input here into wherever we see our input variable for x. All right, and so now that gives me, so order of operation says I have to take care of 2 to the 0 first, right? So that means we have 1/5 times 1, and that gives me just an overall answer, 1/5. All right, that's one way of seeing it. And then the last one here is f of minus 2. Right? This is 1/5 times 2 to the negative 2 power. Okay, and that now means, so at this point I can start picking up the pace a little bit. It's a 1/5 times, so 2 to the negative 2 power is the same as a 1/4. Okay, and so now that means together it's a 1/20 is our final answer for that. All right, 1/20. So that's how we've done part B right here. Once we recognize the form of our function, getting the work done is easy. Okay. And so now in part C of our example, I even want to put in another a problem that will change your understanding. So how about f of x equals minus 5 to the x? It looks a little dangerous because throughout our demonstrations earlier, I mention that something like this, how about minus 3 but in parentheses to the x, is not exponential. Okay, we had this in our demonstration problem earlier to point out which one is exponential and which one is not. As a matter of fact, now I remember this was among one of our earlier examples, example 1. Okay, and so similarly, if this problem was negative 5 in parentheses to the x, then I wouldn't even proceed. Okay, if the problem was negative 5 in parentheses raised to the x right here, I would not proceed. Okay, this is not exponential. However, this one is different. Observation is telling me that the negative 5 is not being put inside the power, inside the parentheses. Okay, so that means the x here is only, the x power here is only the x power for that 5 right there. So what about that negative sign? So really this means, and now I can clear this away. This means it's a negative 1 times 5 to the x. So now we are legally working with an exponential function. The real base is here. It's still a positive base, base 5. The constant coefficient c is a negative 1. C times a to the mx plus b. The a to the mx plus b here is that 5 to the x. Okay, but the c here is a negative 1. All right. And so now in that way, once we clearly see that that nature of our function, so this is now clearly an exponential function. So evaluating f at 2, that means we're looking at negative 1 times 5 to the power 2. And that now means we're looking at, so PEMDAS again is telling me that I have to raise 5 to the negative 2, to the power 2 first, so that's 25, but now multiplying with negative 1, okay, minus 25, or negative 25 is our final answer for that. All right, so this function clearly is an exponential function, once again, because without the parentheses, there's a whole intention. It means it's a negative 1 times with the function 5 to the x. So in the end, the base is still a positive base. Now f of 0, as asked. Okay, now it is going to be negative 1 times 5 to the 0 power. All right, negative 1 times 5 to the 0 power, and that makes it, so negative 1, I didn't get to that yet, but 5 to the 0 power needs to be taken care of before multiplying. So now it's 1. Negative 1 times 1, the answer is negative 1. That's our final answer. All right, and then f of negative 2 right here. Okay, f of negative 2 means here we're looking at negative 1 as the coefficient times 5 to the negative 2. So I just successfully substituted that negative 2 into the place of our x in the function. But that now means to evaluate further, to proceed further, we're looking at negative 1 times 5 times 1 over 5 squared in the denominator, which is a 1 over 25. And then multiply together with a negative 1, it's going to be a negative 1 over 25 right here. All right, that's what it is. All right, last problem in this example 4. All right, so with this last problem in the example 4, let's look at the function as following. F of x equals, how about 2 times 5 to the x, okay, minus 10. 2 times 5 to the x minus 10. So now clearly, see, this is a c in our general form of an exponential function. C times a to the some mx plus b plus k like that. All right, and then so now in that way, this is a k, this is a 2. Our function is quite trivial already. So now f of 2 is 2 times 5 to the power 2 minus 10. But so here we strictly have to follow order of operations. Okay, the order of operations is going pretty heavily in here. So power comes first. So 5 raised to the power 2 happens first. And then we multiply with 2. And then we subtract 10. All right, so here I'm looking at 2 times 25 after raising 5 to that power 2. And then I'm going to subtract 10. So that now gives me, so 2 times 25 is a 50 minus 10 right here. Our final answer is a 40. All right, that's how things happen like that. And now f of 0, okay, so now I'm going to substitute in 0 for x. So 2 times 5 to the 0 minus 10. Okay, so 5 to the 0 is 1. So we have to, again, follow the PEMDAS right here. Power comes first. Power or exponents comes before multiplication and division. I shouldn't even say it comes first, because if there was parentheses, then whatever inside parentheses must come first. But here there wasn't parentheses. So 5 to the 0 is a 1. 1 times 2. So now I'm going to write down the next step. 2 times 1 and minus 10. So 2 times 1 is a 2, and minus 10, that gives me a negative 8. And that's how we know how to lead our own calculation. All right, and then for the next one, f of negative 2. All right, f of negative 2. Just like that, 2 times 5 to the negative 2 power minus 10. Okay, and so that means that this now gives me a 2 times 5 to the negative 2 is the same as a 1 over 25, and then minus 10. And so now I'm looking at 2 over 25 minus 10. All right, And then the final answer allow me to use that other visible space for my the visible space for my other board right there. But this means we have negative 248 right there over 25. That's our final answer for that. All right. So that's how we've done with this part. So I emphasize that throughout this whole problem right here in example, throughout the entire example 4 here, we are exposed to those kind of exponential functions where it's more general. It has coefficients in front of our simple exponential function. It may even have some other constant added to that. Okay, and this kind of general exponential function will be seen even often in the later learning of our later part of our learning about exponential functions. Here they are just simple calculation problem where I want to emphasize the order of operations parameters when things get complicated like this. All right.